So for example 4, we can use the product and the quotient rules. If we look at this first problem carefully, we have the product of x squared and 2 minus x. Both of these are defined for all real numbers. So their limits are going to be defined, and we can rewrite this as the limit as x approaches 3 of x squared times the limit as x approaches 3 of 2 minus x. And let's see, what's that going to be? 9 and -1, so we'll end up getting -9 as our limit. Here, again, we can use the quotient rule as long as the bottom's not 0, and in this case it's not. So we'll have the limit as x approaches 2 of x squared plus 2x plus 4 over the limit as x approaches 2 of x plus 2. And we'll just evaluate them using the substitution rule because, again, these functions are defined at 2, so we can just plug it in. This is going to be 4 plus 4 plus 4, so that's 12 over 4, so 3. Okay, let's move on. So here's a situation where we can't keep doing what we've been doing. We can't use the quotient rule here because the bottom is equal to 0. So we can't say this is not equal to the limit as x approaches 0 of tan of x. Right? We can't do this because the bottom is equal to 0. That's our problem. So we have to get creative, and part of what we're going to be doing through the next couple of weeks is learning techniques for taking limits for problems like this where we can't just plug it in. So in this case, with a trig function, one of the first things we might want to try is modeling this after sine of x over x. One of the things we could do is we could rewrite tangent as sine of x over cosine of x. And then I just, instead of dividing by x, I multiplied by 1 over x just so it wouldn't be quite as confusing. And then we can rearrange this and now we can actually use the product rule because we know the value of this limit. If we didn't know the value of that limit, we couldn't use the product rule, but we talked about the limit as x approaches 0 of sine of x over x already. So we're going to say this is the limit as x approaches 0, sine of x over x times the limit as x approaches 0 of 1 over cosine x. And we know this is 1 times, and the value of cosine at 0 is defined, it's 1, so the limit is 1. Let's look at a graph. Now remember, when we're graphing trig functions, we need to be in radians, so we're going to make sure we switch into radians. We're going to put our function in. So this is going to be tangent x divided by x, and we're going to do zoom z trig, and we'll start with that and see what it looks like. So we can see all those places where the quotient is undefined, but we can also see this area here, which is where we were looking when x is equal to 0, and we can see that from both sides that function appears to be approaching the same value. And let's we'll plug in 0, and we can see it's undefined but if we move just a little bit to the left or right, we're getting 1. So that's the sort of quintessential behavior of this of a limit. We have the function approaching 1, but it doesn't necessarily have to be equal to 1 at that point. Okay. All right. So here they want us to graph to show that this limit does not exist. We can look at it and tell that that might be the case because, again, the bottom is going to be equal to 0 as x approaches 2. So we're not going to be able to use the quotient rule for that. All right, so we'll do x cubed minus 1. Make sure we get the whole thing in parentheses here. Divided by x minus 2. And, oh, probably want to change out a z trig here, so we'll do that real quick. Okay, so let's look at what our window's set at. So let's change this. We'll do just nice increments. We'll do -8 to 8, and let's change by 1 and just see what that looks like. So this here is x equals 2, and we can see the function is going down towards -infinity, and so we would say one of two things. We would say the limit as x approaches 2 of our function does not exist, or we could write the limit as x approaches 2 of our function is equal to -infinity, since it's going down towards -infinity. Okay, you're going to find these situations, functions do not, or the limit does not exist, or the function is approaching infinity or -infinity at vertical asymptotes. So that's a vertical asymptote right there. Unlike the example we saw earlier in the chapter, this cannot be simplified to an extended function. We can't remove that discontinuity, so we end up getting a graph that looks like this. All right, so let's talk about handed limits. So we can have limits that go from the left or the right. So in this case, if we think about approaching a point just from one side, that's a handed limit. So here in the red arrow, we have the limit as x is approaching, let's see what this value is, 3. We're approaching it from the right, or from the side that's larger. So we put a plus sign there. That's not +3. Notice the plus sign is on the other side of the 3. So this means 3 from the right of our function f of x. And here it's equal to the value 3. You can see that right there. Okay. So this means x approaches 3 from the right. So this is a handed limit. And the other arrow down here, this one is saying the limit as x approaches 3 from the left, or from the smaller values. So we put a little negative sign there. That's not -3. That's 3 from the left. F of x. And here it's equal to, if we look, it's approaching this other value 2. This is a step function, or the gradient exponential function. And so we have a jump discontinuity here where the limit from one side is not approaching the same value as the limit from the other side. Just as a note, you can have situations like this where, like, let's say we're on a number line and here's -3. We've got some function and we're approaching like that, that would be the limit as x approaches -3 from the left, and it would look like that. Or if we were coming down this way, this would be the limit as x approaches -3 from the right. So just so you don't get confused about all the positive and negative signs flying around. Okay, so here's a theorem, and it says a function f of x has a limit as x approaches c if and only if the right hand and left hand limits at c exist and are equal. And sometimes this is written IFF, if and only if. And that has a very special meaning. When a function is if and only if, it means that it can be read backwards and still be true. So if we read this backwards, if the limit of a function exists, then its left-hand and right-handed limits will exist and be the same. So that's the opposite of what it said here. Read forwards, we have the right-hand and left-handed limits exist and are equal, and that means that the limit itself exists. Backwards, if the limit exists, then the left and right-handed limits exist and are equal. In debate, people commonly use this as a way to, say, trick their opponent. And a classic example of this is a statement like this. If the fruit is an apple, it is red. Okay, so that's not if and only if, that's just if. If the fruit is an apple, then it is red. The backwards statement of that, if the, we'll just say if it is red, then it is an apple. And that's not necessarily true. So you have to be really careful about this, one, when you're arguing with people or debating with people. If you say a statement and the other person reverses your statement on you to try to show that what you said was false, the burden does not lie on you to prove that the opposite of the statement you said is also correct. So you don't have to even argue that. So keep that in mind. As far as the AP Calc test goes, what you want to be thinking of is when you're presented with these theorems in the book, you need to know the theorems, and what they'll do on the AP Calc test is they'll present you with these types of scenarios backwards and see if you use the theorems incorrectly. So we're going to work on that all year and try to get really good at that. And this is our first sort of insight into that. This theorem can work both ways, but not all theorems can. So we have to really be mindful of that. What I want you guys to do is pause the video now and use what we've talked about to evaluate each of these limits here based on this piecewise function, the graph, and the definition of the piecewise function, and then look back in the notes and see how you did. We're going to go on and talk about the sandwich theorem. Okay, so we want to take this limit, but again, it's a limit that we're not able to do because we don't know the value of sine of 1 over x at 0 because it's not defined at 1 divided by 0. So here's what we'll do. First thing, the sine of any value has a range that is between -1 and 1, right? Sine basically just fluctuates like that between 1 and -1 the whole time. So we know at least that the value of sine can't be greater than 1 or -1. Next, we know that if we multiply sine of 1 over x by x squared and we take the absolute value, that the value has to be at least x squared or smaller, because sine of 1 over x can only be between -1 and 1.